welcome to another episode of the Data Science Decoded podcast. I am here with Mike and Nir, and it's our 20th episode. So congrats to everyone. And Nir, how are you today?
Never better. Very excited about this paper.
Oh yeah, that's your domain. Exactly. Cool.
Yes.
Mike?
I'm okay as well, no complaints. And this paper is quite cool paper, quite deep, mathy paper. I'm not a very big specialist in this specific topic, but I like this stuff. It is a statistical topic, and I think it is a cool paper because it has many interesting interconnections with many interesting stuff. Anyone who does machine learning knows. So stay tuned. We are going to talk about it.
Yeah, thank you, Mike. And nobody asked, but I'll say I'm a little bit under the weather. Thus, I'm drinking some tea. The viewers can see it. But there were some exciting stuff, like I'm following the chess championship, so there was action there. And also I follow UFC. There was a great event, but I won't diverge anymore. To our listeners, the paper today is by Radakrishna Rao from Cramér-Rao Bound. So that's one of the papers on this topic. The title is Information and the Accuracy Attainable in the Estimation of Statistical Parameters. And I'll just say that I stumbled upon the Cramér-Rao Bound while I was in my undergrad doing like random signal stuff, or I don't remember exactly which course, but I didn't remember a lot. So it was interesting to go over the paper. I would say to our listeners, it touches upon our previous episodes, the Fisher one, also the KO divergence from last week, also relates to other episodes we did. So plenty of interesting interconnections with our previous episodes. So we try to build it up and give intuition. And I read about Radakrishna Rao, and he passed away like 11 years ago.
No.
So he was 90 something.
Are you sure?
Yeah, in 2013.
Right.
This paper.
Are you sure? I thought 2023.
Maybe 2023. Yeah, maybe. Yeah. My mistake.
2022 even.
Yeah.
I think it was 2 years ago. 2 years ago, and he lived until the age of 100 plus, even 102, 101, something like that.
Yeah. Thank you for that, Nir. It was a mistake, but the interesting thing, the paper was written or published in 1945, and back then he was still a PhD student under, you know who? Can you guess?
Cramer?
Fisher.
Yeah.
He was a PhD student under Fisher at the time this paper was published.
That doesn't surprise me, but it's nice. By the way, Daniel, can you say maybe just 1 or 2 sentences about how the bound is not called Rao bound but Cramér-Rao bound?
I don't know the reason. Maybe you know.
I don't. I think I read sometime that they both discovered it or derived it
in similar time.
I guess in an uncorrelated manner.
So I would say that I looked into the official. So if you look at the Wikipedia page, the Cramér-Rao Bound, this is the paper by Rao. The Cramér paper, it's even a book, okay, of like 500 pages, which is the one that people cite. So maybe somewhere in the book, he derived it. I'm not sure.
I see.
I chose the paper because it's more concise and we cover papers. So
yeah,
makes more sense.
By the way, I read that this paper was published in India 5 years prior to its publication in Europe, in the United States. I think it was published in 1946 or 1947. So I don't know why it took so much time, but maybe it was 80, 75 years ago. It takes time to know that new interesting paper was published. But it is an interesting piece of information.
Cool. So we're gonna go over the chapters, and again, some of them are quite math heavy, so we won't dive into all the equations, but we'll try to give the motivation and some interconnection between all the things we covered already. So I'll read the introduction, which is interesting. He says, the earliest method of estimation of statistical parameters is the method of least squares due to Markov. And I guess it's regular least squares, right? And he said a set of observations whose expectations are linear functions of a number of unknown parameters being given. So he's just talking about least squares. And again, parameters is, as we talked in the first episode, is the something out there we're trying to estimate. Some specific physical or whatever object in the world.
Actually, Daniel, is quite interesting because I didn't know that Marco was the first who did it.
He's not the first.
It's not
the first. But
yeah.
Due to Markov,
Yeah, I know, but I think that it's attributed to Gauss.
Mm-hmm.
The least squares, the ordinary least squares, as well as the nonlinear least squares, is attributed to Gauss.
Okay.
And then he continues, a significant advance in the theory of estimation is due to Fisher, and he cites the paper we covered in the first episode from 1921, who introduced the concept of consistency, efficiency, and sufficiency. Okay, so to our listeners or who forgot or didn't listen to our first episode, Nir, maybe give us a few sentences about each one.
About what?
Their definitions.
Okay.
What is a consistent estimator? What is efficient estimator? And what is sufficient estimator?
Okay, so consistency is the convergence of the parameter of the estimator to the true parameter in probability.
Mm-hmm.
In probability. Sufficiency is a function of the measurements that is sufficient and capturing all of the information within them.
Information.
And efficiency is back then, before Rao's paper, was the best estimator in terms of mean squared error. And Rao in this paper showed that these efficient estimators are actually the ones that attain his bound, the Rao's bound, right?
Mm-hmm.
And that's it in a few sentences, I guess.
Yeah.
Mike, you want to add something?
No, I think it was self-contained and very well explained. You can't just complement the mathematical definitions. It's just mathematical definitions. So
you saying the definition is sufficient, so you cannot add any more information.
I determined that these definitions were sufficient to define sufficiency, efficiency, and consistency.
Nice.
I would just add that it does relate to our previous episode about chaos divergence, because then, in a sense, if you minimize the divergence, you increase efficiency. Is that a correct claim, Nir? Does it make sense?
Well, yeah. If you minimize the divergence, you're estimating the maximum likelihood. And the maximum likelihood asymptotically is an efficient estimator. Sometimes not even asymptotically, but in the general case, asymptotically.
Okay, so just for our listeners to combine different concepts we covered.
Yes.
But they all relate to a degree to machine learning and what we do. Again, maybe not directly. I would say in my practical work, I never calculated the Cramér-Rao bound.
Okay, I did a lot.
Ever.
Yeah.
Okay, so it's interesting, but let's keep it to the end where we tell our stories.
Yeah.
So let's continue.
One comment, Daniel?
Yeah.
You said the parameters are a quantity we want to estimate. I think that at least in my mind, the way, because I look at neural networks in a different, I guess, magnifying glass than just one who just learned neural networks, because I was heavy into statistics and estimation even before the boom started. So neural networks, for me, we estimate the weights. The weights are these parameters theta for me.
Okay, so you're saying there is a true neural network like somewhere out there, and now we have data and we're trying to estimate it.
Yeah, I guess that's the main it's almost a lemma, right? That neural network is a general approximator of some true function.
Yeah, it's a universal approximator.
Yeah. Universal. Yeah.
By the way, some unrelated comment. I just listened to some very interesting podcast that there are two quite famous sentences about this general universality of the estimator. The one is universal approximation theorem, which tells that you can approximate any continuous, I guess, function with two-layer neural net with some Rayleigh activations, while you need an exponential number of neurons. But there is a second theorem, which is less famous, but turned out that it is quite famous among the experts, that if you have three layers, you can do it as well, but you need only polynomial number of neurons to approximate it. So it's something totally unrelated to this paper, but it just just came to my mind. I don't know why.
Daniel, can you scroll up a few sentences?
Yeah.
Okay, so that's it. So the end of the paragraph there, he's talking about least squares still, and he's saying the validity of this principle arises down there. Arises from the fact that one of the large class of unbiased estimated functions following a normal distribution, the function given by maximizing the probability. Now, he continues, even when the distribution is not normal, the property of minimum variance tends to hold as the size sample is decreased. Is increased.
Yes.
Yeah. And before that, before Fisher, he said there is no assumption about the distribution of the observations except that each has a finite variance. And that is the least squares, the linear regression that I teach, even though I had a lot of discussions, and sometimes heated discussions, with mathematicians or statisticians, let's say, that they are saying that the linear regression has a heterostaticity type of assumption, is a Gaussian assumption, and so on and so on and so forth. But he stated it perfectly that the least squares in the linear regression method that doesn't hold any assumption except the finite variance.
Yeah, interesting.
Yeah.
Okay, I see what you're saying. Okay. And let's continue.
Okay.
Then he says, okay, he's taking the analog of Markov setup. He says ITCAN for 1941 proceeded to find a function t of x1 to xn such that the integral of this t times, I don't know, it's phi of theta times pi times dxi equal to theta. As far as I can tell, this is the concept of consistency, right?
The concept
meaning the expectation of the statistic is equal to the
that's unbiased
theta.
That's unbiasedness.
Unbiasedness, yeah.
It's more stringent than consistency, actually.
Okay. I thought this is consistency.
In this formula, why do you have phi? Is it phi, phi? Why do you need pi? Pi is a distribution of our data points. T
No. Pi is the multiplication of dx1, dx2, dx3, and so on. And and phi is the PDF, is the probability this function.
Yeah, I wasn't sure what pi is. Okay.
Yeah,
Oh,
it
really
took me a while
notation.
to decipher what pi is when I read it. Yeah.
Did you find it by yourself, or do you ask some?
By myself, because it makes sense. It's an n-dimensional integral there, and dxi is just I equals from 1. You see, t is a function of x1 to xn. So they have to multiple all the differentials for this integral. That's the product.
Okay.
But Nir, why do you have phi? What is
phi? Phi is the PDF that is a function of x and theta, and he's just mentioning it's a function of theta because it is. The PDF, it's like f, what we call f, lowercase f.
So, and then I'll continue, guys. It says that the variance, which is t minus theta squared, and again in the same integral, is minimal.
Mm-hmm.
So I thought this is like the idea of efficiency.
Mm-hmm.
So when I was reading, I was thinking, okay, this is consistency, this is efficiency, but you're saying this is unbiasedness, that the estimator is unbiased, and this, how we would call it?
And this variance is minimum mean squared error, right?
It's the minimum square. Yeah.
If this is equal to the 1 over the Fisher information, which is the bound, then it's efficiency.
Then it's efficient.
Yeah.
Got it. Thank you for that.
But Nir, it is really cool that you managed to understand it, because I have almost broken my mind in an attempt to understand what is this damn pi, because I started thinking
it's a circle.
It is not pi. It is not 3.14. But permutation. Wow! It is great.
Yeah, you know that these days it won't fly, this kind of writing.
Sure.
He has at least to define what is pi, at least, or put some indices on this pi.
There is no hint.
No hint. No.
And here he says the claim: the object of the paper is to derive certain inequality relations connecting the elements of the information matrix defined by Fisher and the variances and covariances of the estimating functions. A class of distribution functions which admit estimation of parameters with the minimum possible variance has been discussed. And then he adds, the concept of distance between populations of a given type has been developed starting from a quadratic differential metric defining the element of length. So he's talking about also distance between populations, which again, I'm hearing that. I'm thinking KO divergence.
Mm-hmm.
Yeah.
And again, this is 5 years or 6 years prior to the paper of KO divergence. So of course, he didn't cite it.
Look how many papers are based on Fisher. It's a revolution what Fisher did.
Yeah, I think that's one of the takeaways of the podcast.
Yeah.
Like, it changed so many things.
Yeah.
Okay, now we move into a chapter which is estimation by minimizing variance.
Mm-hmm.
Okay, and again, I don't know if we want to go to the equations, but what I understand he says here that again, if we have thetas, it's the parameters we're trying to estimate, and we build in t, a function, then it says here that like the best estimator, or I don't know if it's the best or efficient, is the one with the smallest variance or something like that, right? This is the claim here.
Yeah, this is 2.2.
Daniel, I think I have a small remark regards the formula beforehand. The formula 2.1.
It's not the same as this one.
No.
It's not totally the same. I think they are related. We will discuss how they are related. But what is written in 2.1 is that for any interval around the real value of the parameter, the probability that this efficient estimator fall into this interval is smaller than the probability of any other.
Yeah, exactly. That's why I thought it means the variance is small.
Yeah, I think
this
this
is like
condition
confidence
is
interval.
stronger than the 2.2.
Yes, it is stronger. And he writes it, by the way. He writes if replace the condition 2.1 by a less stringent one.
Less stringent, yeah.
This is stronger. This is like probability density function type, and this is only the second moment, right?
Yeah.
Okay.
By the way, it is interesting that I took quite many statistical classes throughout my life, and I never came across this 2.1. It is so natural, but it's the first time in my life that I came across this formula. It is more stringent than the variance requirement, but still it is for me it is much more natural.
I agree.
Yeah.
Totally agree. When I see a lot of expectations on stuff, I'm like, okay, like what happened?
Yeah. The problem that 2.1, you can't do anything with it except just look at it.
Yeah.
By the way, here he says where E stands for the mathematical expectation. So he defines what E, which is, we all know it, but why he didn't define.
Yeah.
And then he says we may further assume the property of unbiasedness, meaning the expectation of T is equals to theta. So our statistic converges to the true value. And
Nir, I have a general question to you in this respect. Why are statisticians so obsessed with unbiased estimator? we may have some biased estimator, very small bias, and it can be much better in terms of variance. So why we are so obsessed with this unbiased? Why is it so important from your point of view?
Yeah. So the problem with biased estimators, it's not as easy to derive this bound for biased estimator. There is this bound, the Cramér-Rao bound, in essence, it's derived only for unbiased estimator. And he starts from that. And the reason that we want it to be unbiased is that, at least in the early days, was that it doesn't, the way I explain it to students is that it doesn't really, intuitively, it doesn't make sense that we have a very, very tight, narrow accuracy about a value that is far away from the actual value, right? That's how you basically take the concept of bias into the extreme. But if the bias is really, really close to the actual estimator, there are examples that, like you said, that there are estimators that are better in terms.
Here he says, by the way, exactly that.
Yes,
I'll quote.
Yeah.
There are, however, numerous examples where a slightly biased estimate is preferred to an unbiased estimate with a greater variance. And then he says, until a unified solution of the problem of estimation is set forth, we have to subject the estimation functions to a critical examination as to its bias, variance, and the frequency of a given amount of departure of the estimation function from the parameter before utilizing.
So he's saying, I derived it from unbiased because it's more convenient. That's the underlying message here. But he's saying not any estimator is unbiased, and obviously we have in machine learning we have what we call the bias variance trade-off, and this is exactly it. This is exactly it, right? The mean squared error is the bias squared plus the variance. And
exactly.
Yeah.
And then when I'll ask here a question. Then if the mean square is the squared of the bias and the variance, how does sufficiency come in? You understand my question? Because I feel like the bias and the variance are like mapped to consistency and efficiency, but we also have sufficiency.
So sufficiency.
How would you like combine them?
So he is combining it, I think, here in the paper. Also, there are Blackwell combined it, I think, together with him. I think they call it now Rao-Blackwell or Blackwell-Rao theorem, in which they say that if you have a sufficient statistic, then it's called Rao-Blackwellization. Then you can derive out of this sufficient statistic an estimator that his variance is, or his MSE is lower than the, and you can continue that until you get continue this process until you get a minimum variance estimator. So the sufficiency is important for capturing all the information inside about the parameter inside the data.
Yeah,
that's it.
Yeah. Okay. Thank you for that.
By the way, some small remark maybe for our listeners about bias variance trade-off. In the bias variance trade-off we are using, we in machine learning are doing it based on some data. So we don't know what is the real distribution of our data. So we can't compute this stuff precisely mathematically, because we don't know which function we should put in under the integral. So all these summands, also bias and variance, we can only estimate. So there is no exact math in machine learning in this respect, at least.
Yeah, we have tools like cross validation and etc. to try to estimate those things.
Yes.
Mm-hmm.
Exactly.
Okay, so let's continue to the next chapter. The title is Single Parameter and the Efficiency Attainable. So I think here he derives the Cramér-Rao bound.
Mm-hmm.
Okay, and then he starts with phi of x1 to xn to be the probability density of the observations between x1 to xn. So that's the data we have.
Yeah.
And then t from x1 to xn is the unbiased estimate we build of theta. So it says the integral, and again, over from 1 to n of t times phi is equal to theta, because it's an unbiased estimate. That's the definition.
Yeah.
Okay. Then he says, cool. I have theta on the right side of the equation. I can differentiate by theta, and also the left side, which is an integral, we can differentiate.
Mm-hmm.
So theta becomes 1, and under the integral we now differentiate by theta. So we have d phi d theta.
Mm-hmm.
Okay, because that's the only thing that's affected by theta.
By the way,
yeah.
Some small remark, some mathematics as a former mathematician, you can't always differentiate under integral. Here he writes, if the integral exists, there are some conditions. If even the integral exists, you can't just differentiate under the integral sign. So I don't remember the conditions, but here he states explicitly if the integral exists.
Yeah.
For mathematicians among our listeners.
Yeah, the integral exists, and he's differentiating with respect to a non-integral, a theta that is not a part of the integral at all. And he also omits it, but he uses Leibniz. If you take Leibniz theorem and you use it here, you'll get this.
Yeah,
exactly, Mike. Yeah, when I was in class and the professor proved the Cramér-Rao lower bound on the whiteboard, he used Leibniz.
Yeah.
Okay. Fair enough.
Okay, cool.
By the way,
good that you're mathematicians.
In 3.1 and 3.2, he does actually denote that it's an n-dimensional integral, and he actually just above that defines phi of x1 to xn that it. So there is no. I think that here when it clicked to me that pi is just the product of everything, of all the differentials.
Yeah.
Yeah.
Okay.
And then he used the Cauchy, I think, inequality, right?
Yeah.
And then he can Cauchy-Schwarz.
Yeah.
Again, I don't know where it was, like Fourier analysis or some kind of, or maybe complex numbers. I was taught that. And he says that now.
Daniel, I think it is called Holder inequality in this case. but I'm not sure. May if I'm wrong, I ask our listeners to correct me. I think it is Holder, but maybe
I wrote Cauchy-Schwarz here.
okay.
Because it's the multiplication of two variances is smaller than the covariance.
Yes. But by the way, I don't know if you knew, but Cauchy-Schwarz is one of the most usable or used inequalities in all fields.
Yes.
Interesting. I didn't know that. Again, in my practical work, I never used Cauchy-Schwarz. Okay, so what it says here, under the integral, we have t times the phi to d theta. So he breaks that, and he says like the variance of t times the variance of the phi le d theta divided by phi is smaller or equal to the covariance of t.
It's not small, smaller or equal. Sorry, not smaller.
Yeah. The covariance of t and this d phi to d theta divided by phi squared.
Yes.
And then he can define this variance of d phi to d theta divided by phi as I, which is the Fisher information. And also he writes it's the expectations of the log of phi divided by d theta squared. Again, it dovetails a little bit to KL divergence because we also had like log of the likelihood in the information. So again, it combines here. And he says explicitly, this shows that the variance of any unbiased estimate of theta is greater than the inverse of I, which is the Fisher information, which is defined independently of any method of estimation.
Exactly.
The assumption of the normality of the distribution function of the estimate is not necessary.
No.
Okay, so in theory, we can finish here.
Yes.
Yeah.
Right, this is the bound.
Yes, this is the bound. Yeah.
Give again here, because this is your expertise, give us a few more sentences about the intuition. What happened here? What does it say exactly?
It says that Fisher information is a function of the probability density function of the probability, the cumulative density function, the distribution of the measurements and the hidden unknown parameters, and it does not depend on the way that you're going to estimate the parameters. Okay, it is a function only of this distribution. So there is nothing else you can do to achieve better than this. Now, by carefully manipulating the data, you can maybe achieve this, maybe this bound, but it's not, this bound will again, for unbiased estimator, it's 1 over the Fisher information, which says, okay, with the Fisher information is the amount of intrinsic, he called it here. Can you scroll up a little bit?
Yeah, it says here. Intrinsic accuracy.
Yeah, that's intrinsic accuracy, exactly. And 1 over this will be the bound for any, and now we know to call it precision and not accuracy, for any precision of any estimate. That's it.
I'm trying to understand something. So it says like we have a distribution that is the data generating function.
Yes.
Which is something, again, theoretical, we don't know about it.
Yes, theoretically, no, you don't.
Yeah. So doesn't matter what we do with the data it generates, we can only let's say, minimize the variance to this bound.
Exactly. Yeah.
So as a physicist, I ask, is it like some kind of uncertainty principle, you know, like?
Exactly.
Okay.
Exactly, uncertainty principle, yeah. There is an intrinsic. Intrinsic, it means that it is intrinsic to the distribution function, right? It's a property inherent in the distribution function that it generates data that you can estimate just up to a certain uncertainty, and you can never surpass that in terms of precision.
Yeah.
And that's it.
To me, it's interesting because it's something about the nature of reality. Again, maybe I'm too much of romanticizing the result, but it's something about like a reality, like basic, because it's unrelated to anything we can do.
Yeah, in the realm of probability and probability spaces that we discussed last time, right? With a measure and all that, measure
measure theory.
Yeah, the measure theory and all that in the probability space, the probability density function, the probability rule will dictate how the data is generated, and there inside this rule there is a hidden uncertainty, and you can't get better than that. In some cases you can be exactly that, but that's it.
Perfect.
By the way, for me, I don't have a very deep expertise in it, and the last time I did serious statistics was in 2008, no, 2006, many years ago. But for me, this bound is very natural. Just imagine that these derivatives, it's the extent of how much this probability distribution depends on your parameter. If this probability, let's fix some parameter value. If the probability distribution really depends on the value of its parameter, so we can theoretically at least estimate it very, very precisely. Why? Because this it really depends on this parameter, so we have a good chance to estimate it. And just assume now that this distribution function very weakly depends on it. Okay, so even we have a huge amount of data, the distribution function, the data that we're gonna get will be only weakly depending on this parameter. And it is very natural that in this case the variance of your estimation will be quite high. It really depends on your data, because your data is only weakly depends on theta. So we can get this, so you can get that, which is what weakly dependence is about.
Yes, agreed. Yeah.
Daniel, is this point clear or
no?
No.
I didn't understand.
So
why it's so obvious to you? Like I didn't follow.
Yeah, what Mike is saying is referring to 3.4, and he says okay, the efficient information is the second derivative of log of phi of the f versus d theta squared. By the way, it can also be show that this is equal the first derivative squared, okay, or
yes,
something like that. So if we do,
I was referring to that to the first derivative squared. Thank you that you mentioned this.
Yes, and I know. And when you think about derivative, you say what is the rate of change? Let's say it's a linear, okay?
It's like the curvature. It's the second derivative.
Exactly. What is the rate of change of this function due to the derived parameter? Okay, if it's weakly connected, then the derivative is low. The information is low.
I understand that.
And over the information is high. The variance is high.
That I understand. I didn't understand the, like in nature there's, or in math, whatever, right? There's like a minimal uncertainty that you cannot surpass. I don't see it in this, right?
Okay, well let me explain you. Let me in case that it strongly depends. What does it mean, strongly dependence? It means that if you move your value of a little bit, you will get another distribution. So your data will look very differently. So you're not going to confuse yourself, or at least less. You keep, because you move your value of theta at a very small amount.
It's like sensitivity, right? It's
yes. So and this means that based on your data, which is really depends on your on theta, you can, in this case of strongly dependence, you can estimate your theta with a very small variance, because if you move your theta in a little small amount, left to the left to the right, you will get a totally different distribution, meaning that you get totally different data. So in some sense, which theta is very sensitive to data. So your data is determines this theta in a greater extent than in the case of weak dependence.
Yeah, I thought that what confuses me is, again, previous chapter we had KO divergence. I can minimize it to be 0, right? Same distribution, right? And then I would.
Your error?
Hmm?
What do you mean? What can you minimize? You mean a log likelihood distribution?
Yeah.
You can minimize it until it reaches a minimum. It doesn't have to be 0, Daniel.
That's true.
Sometimes it can be 0, but when it's 0, it means that you met the bound. That's what it means.
Yeah, exactly. But I thought when like 0, you're right. 0 is the bound.
No. Yeah. The bound is not 0 in a general case.
No. Yeah. I mean this.
Maybe
this case. Okay.
Like that. Yeah.
Okay. So let's continue.
Okay.
So we'll go over the paper. I just want to say that at some point here, next chapter is case of several parameters.
Mm-hmm.
We can continue. I want to touch the last episode, last chapters.
But by the way, just for the listeners, this one parameter and several parameters in estimation theory course, it's between 9 to 12 hours of lecture, just to prove it. So we're not gonna cover it here.
And it introduces the Fisher matrix, right?
Yeah.
Because now we have here.
Yeah, Fisher information matrix, FIM.
By the way, I just checked in Wikipedia. There is some bound. I'm not sure it is called the Rao-Cramer for the based estimator as well. It just looks different.
It's Bhattacharya or something. No.
It's also Cramér-Rao extended for bias. Yeah.
Yes, Cramér-Rao for the bound for unbiased estimator.
Yes.
Okay, so here that's the few last chapters I want to cover. So it's called the population space. So he says, okay, we have theta, and let's say we have q of those, q of parameters we're trying to estimate. So all the possible parameters, they build a space, and he called it the population space. And then in this space, he defines a distance metric.
That's exactly what Mike was talking about 5 minutes ago. If you change theta by d theta, what is the distance between these two distributions? Is it large or is it small?
And if it is large, then a small change in theta causes a very big change in the distribution of x, and it also holds converse direction. And
then he continues in the next chapter, the distance between two populations, which again, it's interesting because we talked about KO divergence. We also did similar things in the K nearest neighbors, right? Also with two populations. So he says here, if two populations are represented by 2 points, A and B in this space, then we can find the distance between A and A, B by integrating along a geodesic using the element of length.
By the way, I'll try to explain it a bit into a bit of simpler language, at least from my perspective. Here we are talking about what are actually points here. The points here are two different values of theta, two different values of parameter
of possible estimators.
Of possible estimators, and he's trying to define some distance in this let's call space. I think if I hope I'm not wrong. I think it defines some kind of Riemannian geometry. But
he said it here. It's a Riemannian space here.
I admit I didn't see that. I just remember it from 2005, and then I learned it. And in this respect, this Fisher information defines some distance in this space, and also there is some addition to it, and how it relates to something that we sometimes use in machine learning, natural gradient. And natural gradient, if is one of the methods which use Fisher matrix
Fisher,
as a normalizing matrix to because if you don't use this, why does it called natural? It's called natural because it is invariant to scale. For example, if you just take your parameter and multiply it by 10, and then you continue doing your gradient descent and not natural descent, then all these scales will change, and then you're using this Fisher matrix and you normalize all your estimation, the determinant of this Fisher matrix. You are not sensitive to any transformation, to any, let's say, differential transformation of your parameters. And then this is the reason it is called the natural gradient. And this is one more applications of Fisher matrix. By the way, it is used, at least it was used in reinforcement learning. There is some method before proximal policy optimization. I don't know its name. Something in the word region is in this name. It was a quite popular method before all these PPO and DPO methods in reinforcement learning. But the problem in this method, that this feature transformation matrix is very hard to estimate, and this is the reason why it is not widely used. Yeah, it was a long remark.
First, thank you for that. I also had some thoughts about it. I would just add, so in order to get the Fisher information matrix, which is information about estimators, you have to use estimators. So then, did somebody did this infinite regression of using a Fisher information matrix on the information matrix on the infinite?
Yeah, it is some kind. It is some kind of
I don't know. I'm joking. I don't know if it does. If it even makes sense.
It is not the case. It is not the case. It is not actually the case. I'm joking as well. But there is, if you assume some form of this f, and this f is usually parameterized in machine learning, deep learning, by some neural net, the differentiating of your neural net is not so simple. The problem all these estimates is the large variance. Okay, and you can just estimate Fisher matrix and use natural gradient when your estimate has a very large variance. So it is not so simple. I remember that the big variance is the main problem, but maybe there are more problems with that. The fact it is almost not used, at least now.
Perfect, and I think this is our last chapter. The title is Distance in Tests of Significance and Classification. And he says, the necessity for the introduction of a suitable measure of distance between two populations arises when the position of a population with respect to an assigned set of characteristics of a given population or with respect to a number of population has to be studied. And the first problem is the significant. And the second significance, and the second problem is classification. Okay, so again, significance is related to significant testing. We did one paper, right, from 1935, one of the first episodes. And the idea here, you have an hypothesis, and then you have data, and you want to accept or reject it. And one way he says here, let's use this distance metric in this parameter space in order to do hypothesis testing. And another important part is the classification. Let's see where he talks about it. Here, the estimated distance can also be used to the problem of classification. It usually becomes necessary to know whether a certain population is closer to one of a number of given populations when it is known that populations are all different from one another. Okay, and here he talks about the Mahalanobis distance. We talked about it last week also. And I think he would be happy with the KL divergence if he have heard about it. as a better way to do it. But again, it aligns nicely with our previous episode. That's my the thing that I wanted to say here. You have any other remarks on this chapter?
Yeah, definitely. This chapter is introducing what we now call the Rao test, which is a
I didn't know about it. Okay.
very famous test in statistics, and it has very nice. We will call it asymptotically consistent test statistic.
So it's for hypothesis testing, right?
Yeah, it's the it's defining the hypothesis. The hypothesis is are there set of parameters we are observing is close to a set of parameters we know, or in let's say two Gaussians, are the mu and the sigma close to each other? Okay,
Yeah,
that's what we're testing for, and this test is very, very sensitive in terms of it has feature information inside, and it's very sensitive to the distance. And this is exactly what Mike told us before. Like there is theta plus theta just above 8.8, right? And that's exactly how far the test is reacting to a small change in theta, and it's reacting very, very strongly. This test, and it's a very nice test if you have a lot of measurements.
Nino, but I have a question to you. You have dozens, maybe 100 types of divergences or distances between probability distribution. You have something which is called T divergences, I guess, and there are dozens of types. So distance between two distributions can be probably anything, and it depends how you define this distance. You can define it in many ways.
Right.
As my question is, why this Rao method is better than Jensen-Shannon convergence or Earth-Mover the divergence or Earth-Mover distance and distances like that? Why?
Yeah. So the Rao test is a test for saying is theta equals theta 0, theta naught. That's it. That's the null hypothesis. Okay, so it is a distance in a way, but it's not a distance between it's not a general distance between distributions. It is only checking whether this distribution has the same set of parameters or not. That's it.
Yeah.
Okay.
I see.
And it is shown to be a optimal, quote unquote, test if the number of measurements is going to infinity. It is not so accurate if you have only just a few measurements.
I see.
So it's not better than other tests. It depends when you can use it, but under certain conditions.
By the way, one of the names mentioned here, Bhattacharya. It has some divergence on his name.
Yes. Also a bound. It's called Bhattacharya.
Yeah, but I remember I learned the Bhattacharya bound. I don't remember what it means, but
me too.
Oh, I have a question, guys.
Yeah.
Can you go up? Just that's it. Aitken 1941 on estimation of statistical parameters. Maybe we should look into that in terms of one of the next episodes. I never formally learned Aitken. I learned Aitken method only in numerical analysis course.
Interesting. Yeah, I never heard about him.
Yeah, me too.
And the professor, he was an old professor. He told me Aitken does not get the recognition he deserved. That's what he told me back then. So that's why he is he taught it in his course. But maybe
so I'll look at the paper. If it makes sense, that's a good candidate. As we finish going over the paper, I would like to ask you about when have you used Cramér-Rao Bound in your work? That's an interesting question.
You mean me?
Yeah,
me?
you're the estimation guy.
Oh yeah, all the time, all the time. We use it in if we have estimator for the radar range, okay? Like the range of the target from the radar. How accurate are we? We measure it with respect to the bound. Same for Doppler. Same for angle.
But the bound is on the variance.
The bound is on the mean squared error of the estimator. So let's say that we have, and now it's also connecting to the simulation or the Monte Carlo method that we covered. I don't know, a few episodes back. But if we simulate a full radar system or LiDAR system, I did it both for LiDAR and radar. We want to quantify how good are we in our estimations. Let's say we're taking an FFT and we're estimating the peak of the FFT. How good are we to the best possible outcome versus the best possible outcome, which is the bound? Okay, that's one. Second, when we track targets through space, we usually use the Kalman filter because it's the most lean Bayesian, iterative Bayesian method of predicting something, and it's highly dependent on the covariances or covariance matrices there. But when we measure, let's say, a target with range and Doppler, and we want to track them through time, then we have to estimate the variance for the range and the variance for the Doppler in order to introduce it to the Kalman filter. How do we do that? Usually we take the bound and we multiply it by 5 or 6 or whatever. Okay?
Interesting.
Because we don't really know the variance.
Okay.
Thank you. And Mike, did you have any chance except studying?
I'm working in estimation as well, but I'm estimating stuff in a bit different way, not in the way Nir is doing it. I'm not working in a signal processing domain many years, and then I was working there. I don't think I use it, but maybe in future.
Yeah, I just enjoyed it because it connects so many concepts, and all of those, let's say each concept is like a prism. You can look at the problem.
Yes.
Right. So at the end, let's say we do machine learning, but a lot of it is estimation. Yeah, Mike.
By the way, one small thing, and just recovered from my mind. We're talking about Fisher information matrix, and Fisher information matrix is related to logarithm of to the log of distribution of the density function, and if you think about it, what we are doing in diffusion models, we are just estimating one of the generalization of diffusion models, or diffusion models one of the way to tackle this score function minimization. What is score function? Score function is just logarithm of your density function. We are trying, and then we are trying to maximize. Okay, and I think that I'm not sure this Rao-Cramér bound is used in the generative diffusion models, but I'm sure, and I saw it in many papers, that Fisher information matrix is there. It's for 100%. So it is some relation not to the formula itself, but one of the ingredients of the formula. So
Yeah.
Perfect. Okay, so thank you again. I read the paper, but after discussing it with you, I understood so many more things. So appreciated. And I'll say thank you to our listeners. Hit the like button, etc. And I guess I see you next time.
Bye, guys.
Thank you. Bye bye. Bye bye.